Hi team, another AMP lecture here from Craig. This one is the skeletal system. It's the second in our AMP presentation list, and this one is obviously all about the human skeleton and the bones found within. Today we're going to be looking at a number of things, including the different types of bones found within the skeleton, the functions of those bones, with a particular reference to their use during exercise and how we can maintain them. So we'll crack in. Let's start with the functions of the skeletal system. There's some obvious ones there that you guys are probably aware of, but some less obvious ones too. We'll crack through 5 different ones here. So firstly, support. The skeleton gives our body its structure. It determines the dimensions of your body in terms of height and breadth. The lower limbs support the upper torso. The spine obviously supports the head, and the framework of the ribs provides attachments for the arms to suspend off. The long lever-based bones of the human body, primarily found in the arms and legs, are responsible for movement. They can't do that without muscle attachment, so muscles attach via tendons to these and allow us to manipulate our environment and transport ourselves from A to B. Protection is a key function of bone. The obvious protection bones are those that surround soft inner organs of the body. So we could start with the rib cage there. We have the lungs, the heart, and the upper digestive tract under there. We have the brain being encased in a bony sphere known as the skull and cranium. And we also have the pelvis down here, which strangely protects from behind some of the more precious organs in the human body. Some of the less known functions are those that occur within bone or as bone itself. One of those is blood cell formation, and that happens in the marrow found within bone. Contrary to popular belief, it's not throughout the entire adult body where marrow is producing these blood cells. It's typically found within the axis of the human skeleton, which is made up of the cranium, the spine, the sternum, and the rib cage. So that's typically where you're going to find hemopoietic marrow, which is where primarily red blood cell production occurs. In children, you will find active marrow producing blood cells within the long bones of the arms and legs also. And in oldies, interestingly, that marrow turns to fat, and is known as gelatinous marrow, which can go a little manky over time, akin to rotting fat within some brittle bone, which is not a good framework for stability. Finally, storage. It is the main mineral storage side of the human body. Bone is an active entity. It's not a non-changing structure, so it's constantly ebbing and flowing in terms of the amount of mineral deposition that's found within bone. And that's really dependent on how much you're doing from a physical standpoint. So if you place your bones under stress, they tend to respond by becoming denser and more mineralized. And if you don't, then the body will forego its need to lay down additional bone, and you'll end up with weaker and more fragile bones. Just going to skip by that video of the lady in her Star Trek uniform. She's talking about the different bones that you can find within the skeleton. It's a useful little video, but you can check that out in the full Prezi that's also attached on the Moodle site, and you can work through that at your own pace and watch those videos. But in order to keep this video lecture truncated, so keep your attention, we've decided to forego playing those videos on this particular video entry. So we'll look at them in picture form real quick. You can see there are many bones of the human body. We're not interested in all of them. Why, as a PT, would you want to know bone location and bone ID? And that's pretty obvious. Muscles attached to bone. You want to get a firm understanding of where the muscle originates from on the skeleton and where it attaches at its insertion point. And from there you get a better understanding of the shape of muscle and how it affects the skeleton and moves our extremities and our torso into different positions. And once you understand that fully, you're in a much better place to understand how to target certain muscles with different forms of exercise. and also how adaptations made to common exercises target different aspects of the muscle via the plane in which we move. So you'll see that the difference in coloration here, it shows the bony coloured axis bones there that I talked about before, the rib cage, the spine, and the skull. And then we see the darker coloured appendicular skeleton, which is these long bones of the arms and legs, and also the bones that we find in the hands and feet. Back view shows the same thing from a posterior view here, and of course you can see the scapula on this one here, the back of the pelvis, and also the back of the other long bones there too. So we'll get to know them a bit better as we go through this process. This list here, which is found in your course booklet, gives you an overview of the key bones I would be expecting you guys to be really familiar with. These obviously provide the key points of attachment for the major muscles that we're going to be learning. So it's important that you, A, know these bones by location, B, know how to say them. Nothing sounds less professional than people getting words wrong, so you can listen back to this lecture when I talk through some of these, and you'll hear the pronunciation there. You'll see the middle row of this box here also denotes whether it's axial or appendicular. So the 4 axial bones, just to recap, are cranium, the sternum, the ribs, and the vertebrae. Everything else is considered appendicular, and that is of course attached to one of those axial bones, directly or indirectly. The second process of classification is usually to do with bone shape, and you can see 5 shapes identified here: flat, long, short, irregular, and then the single one here called a sesamoid bone, which we'll discuss. Let's have a look at these shapes then. So long bones are obviously called long bones because they're long in nature. You would generally find them in arms and legs, but there are some smaller ones that you may not have realised are considered long bones as well, and those are typically found within the feet and the hands. So bones of the upper arm, the humerus, and then the forearm, the radius and ulna, would be considered long bones. You've got the largest bone in the body, the femur, along with the lower limb, tibia and fibula bones. And then some other bones you may not be familiar with, the metacarpals. These are the long bones found under the skin of the main hand. I can take you back to the picture here, and these would be these bones here found underneath the skin of the hand, not the fingers, but the long bones found from the wrist to where the fingers start, that main knuckle of the fingers. And then again, down here in the foot, we're talking the long bones that are found between the ankle and the toes. They would be known as metatarsals. Short bones are fairly few in the body. They're typically found in the wrist and the ankle. They're known as carpals and tarsals. And these don't move very much, and they have very strong network of ligaments which keep them pretty close together, but they can move in any direction a small amount, and that enables you to mould your hands and feet over uneven surfaces, or to pick up objects that are round or unusually shaped, like a jar of something or a ball, with your hand. It also allows you to give while running on uneven ground, so that we don't succumb to the forces and get injuries there. We have a little bit of give within these bones. So yeah, useful little bones, as I say, found within the wrist and the ankle. Flat bones are primarily concerned with 2 things. One is protection, so they may cover areas that are otherwise could be compromised from outside forces. And secondarily, they often have these bony ridges and lines on them here, which allow multiple points of attachment for musculature. So the scapula is a great example of this. You can see here the scapular spine, superior angle up the top here. These all allow for different points of attachment to occur for different muscle groups, which gives the shoulders its range of motion, which is second to none in the human body, and the ability to flex and extend and abduct and circumduct only comes about because of the multitude of muscles that can attach from different angles to the structure here and allow all of those actions to happen. Other ones that would be included in the flat bone stakes would be the cranium, the ribs, the sternum, the scapula, and the pelvis. Now, some of these don't appear very flat. Ribs, some might argue, well, how is a rib considered to be a flat bone when it looks long when you look at it? It's actually not just about the shape of the bone that determines its type. It's also the way in which the bone forms. And if you were to saw through a rib, you would see a very different inside to what you would see in a humerus or a femur. Sawing through a rib bone would actually show you that there is a sandwich of what we call spongy bone in the center that is almost solid. So there's no hole, there's no cylinder or marrow space found within that bone. It's a solid structure. Whereas if you saw through a humerus or another long bone, you'll see that there's actually a hollow space in there. So that really helps distinguish between the two. And you'll see that long bone structure soon in an upcoming slide. So if a bone doesn't fit into one of those other categories, if it's not flat, if it's not long, and it's not short, then it's termed an irregular bone. And there are a few of these in the body, and there's a couple of examples on the screen right now. The vertebrae are a great example. Primary role is obviously to protect the spinal cord, which runs through this portion here. Okay, and you can see it also has these little points of attachment here, these little grey areas. This is cartilage, which allows other bones to articulate and move and connect to it. And in this case, if this was a lumbar vertebrae, these might receive the ribs, which could then articulate with that. And obviously they articulate with the bones, the other vertebrae that are above and below as well. The sphenoid bone, interesting one in the mid-skull. If you were to cleave at the top of your head off and pull the brain out of someone, this is what the brain would be sitting on effectively. So through the middle here would be where the spinal cord runs through, and here would be main arteries, veins, and some other nerves that would be running up through there as well. And these little sockets here are where the cerebellum at the base of the brain would actually be cupped. There is one more bone classification, and that was the sesamoid bone. And on the list you would have seen the patella is listed as a sesamoid bone. The thing about sesamoid bones is we're not typically born with them. These are bones which are formed from within a tendon, usually due to repeated stress. And if you think of the knees, particularly as an area that gets repeated stress early in your life, as you learn to crawl, as you stand and fall on your knees repetitively, the calcification that occurs within that tendon is there obviously as a means of protection over an otherwise unguarded sort of area that is prone to a lot of stress. So your patellas are very unique. They're kind of like fingerprints. No one has exactly the same patella because no one has exactly the same upbringing in terms of how early they start walking and crawling and how long they spend doing those things. So, a fairly unique bone in the human body. The spine is another unique set of bones, and it has a critical role of protecting your spinal cord. It also provides, I guess, the main structural element of our torso, so everything else is effectively reliant on the spine to keep its posture so that we can maintain movements of the other appendicular bones that hang off the structure. So we'll dive in and have a wee look at this. You can see it's obviously not just one long bone series. It's a interconnected number of bones. There are 33 in total, and we see it stretched out on the picture here, that they have their own labels. Cervical at the top, thoracic, lumbar, the sacrum and the coccyx. And each of them has a number of vertebrae associated with it, and the location of these vertebrae is often denoted by the first letter of the vertebra group along with the number of vertebrae along the chain. So it always starts at 1 and then moves down, denoting the number of vertebrae found within that region. So the first is cervical. You can see there are 7 vertebrae found within the cervical vertebrae group. That basically comprises your neck. There are 2 key ones at the top here, the atlas and the axis, known as C1 and 2. Now C1 is a hinge type joint which is responsible for the yes or nodding movement of the head, so the flexion and extension of the head, forward and back. And then the axis is a pivot joint, which is where we rotate our head side to side. So I guess you could call it the no joint. So two independently operated vertebrae there. The neck obviously has quite good movement associated with it. We can turn it, we can flex and extend it, move one ear over to one shoulder. So it has a wide range of movements associated with it that some of the other vertebrae don't have. The thoracic vertebrae, there are 12 in total, and that's representative of what it connects with, and that is the rib cage, where there are 12 pairs of ribs that connect in to the facets of these vertebrae here. And this one is a little bit immovable because of the ribs, so you can't really flex, extend, or rotate this area too much because the ribs are preventing that. The lumbar vertebrae, L1 to L5, are the largest of the vertebrae because they receive the most load in standing, sitting, and movement. So they absorb that shock and that load that comes through the spine, and have to be able to withstand that to protect that spinal cord again. Most commonly injured area, typically L4 to L5 and L5 to S1. It's where most lower back pain originates from. And then we have these two structures down the bottom here, the sacrum and the coccyx. The sacrum, this triangular shaped bone at the base of the spine, starts as 5 independent vertebrae, but quickly fuses as you go through puberty into one bone structure known as the sacrum. The coccyx also, the tailbone it's known as, starts as 4 independent vertebrae, sort of remnants of reptilian life, I guess, in involvement, where we might have had a tail at one stage. These fuse typically towards the sort of mid-20s to 30s into one rigid structure called the tailbone or coccyx. The structure of the spinal vertebrae differs depending on where in the vertebrae they sit. We're looking at some lumbar vertebrae in this picture here. You can see L1, 2, and 3. The bodies of the vertebrae are these thick cylinders, and they're designed to take the majority of the force that is put through the spine. You can see here that 84% of the load of the body is supposed to go through these bodies, and that force is somewhat dissipated by these spinal discs that you see here, known as intervertebral discs. So they cushion and absorb some of that shock. You'll notice that the facets here and the spinous processes that stick out the back don't have any of that added protection, and that's why they're not designed really to take a lot of force. Only about 16% of the load of the body is dissipated through those joints there. Now that's, of course, if your vertebral structure is sound and has good posture. And the problem with poor posture, particularly an overly curving lower back, known as lordosis, is that a lot of that gravitational force line is pushed backwards behind the spine and onto these facet joints, which are not designed to take that kind of load, and you can get some fractures of the arches here, which can lead to compression of nerves and back pain that may radiate down through the legs and prevent you from doing any meaningful activity. So posture plays a really important role in this, and this is something we'll talk about when we get on to muscles in A&P. The discs themselves, found between the bodies of the vertebrae, made up of fibrocartilage rings that you can see here, and a watery substance in the middle, offering a sort of cushion. Now, the water doesn't stay in the middle there. Through the day as you load, it will seep into the fibrocartilage rings, which means they flatten somewhat during the day. And that means that if you're loaded throughout the day and on your feet a lot, you will be fractionally shorter at the end of the day than you were at the start. They make up about a quarter of the length of the spine, and are obviously really important to stop bone from grinding on bone in a loaded state. So we're going to talk now about the structure of bones and the type of bone found within the different bones of the body. And the one that we're primarily interested in is the long bone. That's because in terms of exercise, these are found in the arms and legs and are primary targets, I guess, of most gym-based work that we do. So let's have a look at these guys here. First thing to note is there are some technical terms surrounding the different parts of the bone here. You can see the epiphysis at the top here. That just simply means the end, the wider end portion that I'm circling up here. We have one at the bottom, one at the top. And then we have the diaphysis, which would be more commonly known as the shaft of the bone, which is the narrower cylindrical shape part. And as I mentioned earlier, long bones have sort of a hollow portion through the middle here, which initially is where bone marrow would be stored, but you can see in this picture, bone marrow is actually represented by the red that's found within the what we call spongy bone at the ends of the bone here, and this yellow you can see here is the fat that I talked about depositing in the bone as you reach adulthood. So what do we find within this bone? We find spongy bone within the epiphyses or ends where the marrow is stored, and we find a layer of what's called articular cartilage here that runs along the top of the end of the bone here, and that's to prevent this bone in its joint from rubbing against another bone in the joint. So if we use the example of the elbow, we would be talking about the humerus at one end obviously, and then the ulna meeting that at the elbow, and we wouldn't want those two grinding their bone surfaces together, so we have this layer of articular cartilage over the top which helps to separate and to cushion that meeting between the two bones. The heads and the shafts, the epiphyses and the diaphysis, are separated by this line that you can see here. That's known as the epiphyseal plate or growth plate. It's an active plate when you're growing, but when you're fully mature, that just fuses into bone, and that's what you're looking at in this picture, the fully mature long bone. You can see just a white line representing that growth plate. We'll talk more about its role shortly. The diaphysis or shaft has a couple of layers to it too. We have an outside, almost skin type layer. You can see it here with the blood vessels coming into it here. It grafts onto the bone. It's known as the periosteum, and that's where the blood network is able to enter and attach to bone before penetrating its way in. Underneath that, you'll find the strongest bone that we have in our body, which is this white portion here, and this is called compact bone. And this compact bone is really what determines the density of the bone. The thicker that compact bone is, then the more dense and the stronger your bones will become. So when we talk about adding bone density by doing exercise or reducing bone density by not doing exercise, this is really what we're talking about, the width that is found between the cavity in the middle here and the outside edge. The medullary cavity through the middle here is obviously the marrow storage site when you're growing, and then becomes that fat storage site through the middle there. You'll see that blood has access to the middle, and that's really important when you're growing obviously, because that's where the new blood cells are being produced, and blood has to make its way in to get those new blood cells and circulate them around the system. So on the right you can see a picture of a real bone. It's obviously been sawn open for you to have a look at, and you can see the density of the spongy bone within there. There is majority white with some little pores within it where that bone marrow would reside. So known as spongy bone or trabeculae. This also has a very important role in the joint. It's the bone structure within the joint obviously, and because it is porous and it does have more holes than compact bone, if bone density was to diminish, these holes would effectively get bigger and bigger, compromising the stability and the amount of force that the bone can withstand. And this is typically what we talk about when we hear about hip replacements, knee replacements and those kind of things. It's where a fracture or a shattering occurs in the spongy bone end of the epiphyses, and it needs to be replaced mechanically. And it is quite a gruesome process. It's much like carpentry, where effectively a ball with a rod on it would be hammered into place and to replace this end of the epiphysis of the bone. Like I said, the ends of this bone would be covered in articular cartilage to prevent it from grinding against the bone in the joint. The picture that you're seeing now is an example of an osteoporotic bone, so a bone that has gone through the bone wasting process, and that is not going to be able to withstand much force at all, and you can see why a shattering could occur, and that would be a prime candidate for a hip replacement or a knee replacement, depending on where this is. So spongy bone is thin layers of bone, and of course we've got the marrow that's found in between them there, and you'll see a wee video on this in the main presentation that's found on Moodle. I'm not going to go through the whole thing today, but you'll actually see how this bone is formed and made and its location within the bone. The epiphyseal plates or growth plates, you can see clearly on the picture there, this would obviously be a child's X-ray, and you can see very clearly that there are almost two bone structures here separated by a thin line of cartilage, and it's this line of cartilage that actually continues to grow bone so that your bones grow in length throughout your maturation phase. Separating these two bony sections here would have dire consequences, obviously, in terms of growth, and would lead to a shortening of one limb over another. So, just to recap, the diaphyseal shaft has those key layers, the periosteum, the outside sort of layer that allows the blood vessels, nerves, and other things to arrive at the bone. You've got the compact bone layer, which helps us withstand force, okay? And then we have the cavity in the middle, which is the where the marrow is stored through those initial years. And there's the overall picture of it again. Now, obviously, from a fracture perspective, any cracking to a bone surface would be considered a fracture. This compact bone area here is most at risk because obviously it's the thinnest portion of the bone. And if a minor cracking was to occur to one side of this here, that would be considered a fracture. And of course, if it goes right through to the marrow cavity, there's a good chance that it would break all the way through, and that would lead to a clean break. So we'll talk about a wee bit about how bones develop and how they grow. So about 6 weeks as a fetus within the womb, you'll start to begin the bone formation process, and that will continue laying down bone until around 25 years of age. And that number's under a little debate at the moment. It's thought that, in particularly females, that peak bone mass window of opportunity you have to lay that bone down is actually reducing significantly. So it's thought actually a lot of females are reaching peak bone mass between sort of 16 and 18 years of age, which means you've really got to take advantage of the window of opportunity you have to lay down bone in those early years. And obviously, when you're talking teenage girls, there can be a tendency to diet and avoid high-fat products and those kind of things, and often they can be dairy and calcium-containing products, which would not be a great thing. So ossification is the term for bone growth, and it occurs in a couple of different stages. There's first primary ossification and then secondary ossification. I'm going to talk you through them briefly. And there is a great little video on the Moodle site as part of the main presentation that you can have a look at after this and see the process in action. It's pretty cool. So we'll skip past that process here. So, growth of bones. Let's say we're looking at a baby in the fetus, in the old fetal position within the mum, and we start with a blob of cartilage effectively. So there's a blob of cartilage that represents the sort of shape of the bone to come. First thing that will happen in that cartilage is in the center of that model, some cartilage cells called chondrocytes will begin to multiply and swell. What will then start to occur is spongy bone will be laid down through the middle of the shaft of the bone. So it always starts in the middle here. Blood vessels will penetrate in while it's soft cartilage, and that's what allows access to blood vessels for the remainder of the life cycle. And you can see in the middle here the remnants of the spongy bone that remains from the initial spongy bone that was laid down. So this provides a bit of a framework. The spongy bone is laid down as it heads towards the epiphyseal plates here, and when it reaches those epiphyseal plates, we set up secondary bone-making facilities up here in the epiphyses at the top. At about that point, we would hollow out the middle portion to allow for that marrow cavity to form. And we'll talk about the way in which the bone lays down in just a second. I just want to get an overview of how that process occurs first. So we start by laying down spongy bone through the middle. It migrates towards the end as blood comes in with it, bringing calcium and helping to lay down that bone. And when it reaches towards the ends, we set up our secondary ossification centers in the ends and hollow out the middle so that we can continue to produce bone marrow and store it in there. About the same time, we start to form our periosteum around the outside layer here, and some osteogenic cells lay down along the inner side of this layer of periosteum and actually start to secrete collagen matrix. which then takes calcium from the blood and other minerals and starts to form compact bone along the edges. So you can see the compact bone starting to form down the edges here to provide thickening. And that's going to continue right through the growth cycle, like we say, to somewhere between that 18 and 25 years of age. So these are the guys that effectively make bone. We've got the osteogenic cells, which start the process, and they can conform into osteoblasts. Now, osteoblasts are bone-forming cells, and they lay down collagen, one of the primary structures we have in the human body that makes up all of our body structures. So it starts with collagen, and then we need to add the concrete or the minerals to that, which is going to turn it into bone. So a mixture of the osteoblasts secreting its collagen and the arrival of the calcium and other minerals on top, putting the concrete layer on top of that, and that's how we layer by layer our bone and add to what we've got there. And eventually what happens is that osteoblast will secrete its collagen and surround itself. The calcium and other micronutrients will come and form a concrete sort of layer at the top, and it ends up trapping itself against the bone and becoming an osteocyte, which is a mature bone cell that is actually part of the bone at that point. So the video I'm just bypassing here, guys, I want you to have a look at, and you'll see these little critters, osteoclasts and osteoblasts, going along the bone surface, one laying down bone and making sure that we maintain our bone density, and the other guy, the osteoclast, is actually secreting an enzyme, an acidic enzyme that actually breaks down the minerals and frees them up into the bloodstream again. And that goes back to the point I made before, that it's not just a static structure, bone. It's constantly being updated, it's constantly being stripped and then replaced to cater for other needs within the body. And one of those other needs in the body for calcium is actually muscle contraction. Now, I don't want to go into that too deeply at this point, but without calcium in the muscle, there is no muscular contraction. So it raises the point that if you're doing a lot of activity that involves muscular contraction and you're not consuming calcium on a regular basis, then there's more potential for you to start stripping your bones for the muscular needs, but not laying down any additional calcium on top of that. And that's a fast-track way to ensure that your bones become weaker over time. So let's have a look at those exercise and bone considerations. So firstly, we understand that by placing the bones under mechanical stress encourages the bones to want to regenerate and strengthen. So it's like anything. If you put something under stress that is a living entity, it will always try to adapt to be able to better facilitate that stress. So in the bone sense, if we're stressing it through loaded activity, which would cause bending and compression of bone, that sets off electrical signals within the bone that, hey, this could cause us damage if we're not careful, and if that's going to keep happening on a regular basis, we better lay down some reinforcement. And that's what happens. It would stimulate osteoblast activity, which would lay down new bone, and provided you'd been eating calcium and that was available, would start to strengthen and increase the density of bone. You have to consider, though, that high levels of repetitive stress could actually weaken bone if you're not consuming calcium on a regular basis. So we just talked about that before. If you're doing a lot of muscular contractions, which requires calcium, and you're not replacing and replenishing that in your post-workout feeds and ongoing feeds, then you can run into a situation where you actively strip bone for the uses by muscle. It is also a use it or lose it type structure. So inactivity such as bed rest or wearing a plaster or lack of physical activity will cause a lack of stress to be placed through the bone, and therefore the body sees no reason to maintain all these bone cells that aren't necessary, and will start to, as it's diminished, the bone density will not bother replacing it. So having a plaster on, you may have noticed if you ever had one, it's not only muscle wasting, but up to a third of your bone mass can disappear within a 6-week period of inactivity. And if you don't actively work about trying to get that back, then you could be compromised for life. Along with bone wasting, there must be, along with bone hypertrophy, as long as we're eating the right stuff and putting our bones through stress, yes, we will see bones with greater density. So this is not necessarily something that occurs body-wide. So you will often see denser and more mineralized bones in people that use dominant limbs. So someone who's, say, a pitcher, like this guy in the photo here, if he throws predominantly with his right arm and he consistently puts that stress and load through that, the musculature and the bones on that side would typically be more dense than the other side. Now, to avoid postural issues and to avoid pretty obvious looking discrepancies between left and right sides, that's where cross-training would come in a balanced gym program to try and raise the level of the weaker limb up towards that of the stronger limb as well. There has been some evidence, though, that because this is blood-driven, when I say this, I mean bone development, we know that calcium is secreted or is carried to bone by blood, which means that if you are consuming and if the need and the stimulation occurs within the body, it may affect the total body. And there was an interesting study done about lower and upper body extremities, and they looked at runners in particular, which of course would be putting stress through the lower limbs in particular, and they actually found that by placing stress on those large bones of the lower limbs, it actually caused a bone density increase in most bones of the body, not just in the legs. Of course, the legs had more density laid down than did the upper arms, but interestingly, there was some across the board. However, that hasn't translated well for things like weight training and so on. So if you only do upper body workouts, then I can't guarantee you that you would get some decent density increases in your lower limb bones. So don't skip leg day if you're thinking that. You have to also consider with athletes non-weight bearing exercises or low weight bearing exercises. There are a couple of critical factors that determine whether an exercise is good for bone density. Those are the magnitude of the strain, so how much stress is placed on the bone. So those things that put a lot of stress, like plyometrics and running and heavy weight training, squats and lunges and all those kind of things are going to place a lot of stress through the bone. They have the biggest effect on bone density. Cycling, swimming are more low load orientated exercises and wouldn't put the bones under a similar amount of stress. So you may get muscular adaptation, but probably not bone adaptation based on those exercises. The other factors that affect things are the velocity of the strain, so how quickly it's applied. So again, things like plyometrics done really fast and explosively, playing basketball and volleyball, those would be things that put a lot of strain and force through the bone. And then the third part that can impact on bone density is the frequency and how often you do these things. So if you think of a running-based sport, there's a hell of a lot of steps taken, done at high intensities and done with a lot of load. Whereas swimming only has one part of the puzzle. It doesn't have a lot of magnitude of strain. It doesn't have a lot of velocity associated with it. It just has the frequency, and frequency alone wouldn't be enough to stimulate bone density. So again, it raises the point of cross-training and why swimmers and why cyclists and those guys should do some cross-training in the form of weighted exercise, whether that be resistance-based training or running simply, to make sure they maintain their bone density. And then, of course, if you don't use it, it can waste away quite quickly, as I mentioned. So bone demineralization is a serious problem for the elderly. Bone mineralization is not only dependent on the exercise and activity and the diet, but also on your hormonal levels. And the bone growth is really determined by some key hormonal factors there, predominantly growth hormone and testosterone and estrogen. And what we know is that as we age, our levels of those hormones circulating in our body diminish year by year, which means that we will all suffer from demineralization of bones. And that's called osteopenia, and it's perfectly normal, provided you have laid down some good bone banks to start with. But if you haven't, and then you go through the process of osteopenia, then there's a very good chance that you would go into a more serious bone demineralization problem called osteoporosis, where it actually affects the function of your bone on a day-to-day basis and your ability to move around. So, really important to front load and make sure that we lay down good bone banks through our growing years, through doing loaded exercise, eating a calcium-rich diet, and making sure that we do everything we can to build as much bone as we can, knowing that we are going to lose it as we age. Now females, this is more predominant in females because they go through something called menopause, and menopause is where basically the sex hormones that they produce bottom out at that point, and from that point on it's going to be a pretty serious downward slope in terms of bone mineralization for females. Men, we keep kicking testosterone out for much longer in our life cycle, which is a lucky thing for us, and it means that we're less at risk of osteoporosis. Unfortunately for the oldies, if they become bedridden through a fall or something like that, then things can progress really, really rapidly at that point. And in 4 to 6 weeks of inactivity, we're really reducing our bone density down to critical levels at that point. So osteoporosis, you can see there again a couple of pictures here between the normal bone matrix of spongy bone and the osteoporotic one. You can see that this isn't going to be able to withstand much force. It's usually, in the case of a hip replacement, this area here, the neck of the femur here, that would snap off, requiring a new synthetic version to be attached on. It's pretty amazing what can happen these days in terms of surgery, and you can give a person a new lease of life with a new replacement joint, and they can get back into stuff and live a normal and prosperous life. So, yep, just mentioning those peaks again, this is probably from the World Health Organization figures. Just a reminder that recent research is suggesting that for females in particular, that these numbers are coming down in terms of the ability to lay down those bone banks. So many of you guys are in that zone right now that is critical, and we should be looking at our diet to ensure that we get the necessary 2 to 3 serves of calcium-containing foods in our diet going forward. And of course, exercise, but we're all doing that, right? Okay guys, so that's the end of the video lecture here. Just a reminder again, go back to the full Prezi that you can work through at your own pace and have a look at some of those videos that I've talked about. I'll also be doing some recaps in class in the preparation for our end of topic quiz. The end of topic quiz can be found on the Moodle website as well, and when you feel like you're ready to have a crack at that short answer online quiz, then you can do so. A bit more information will be given in class. Thanks for listening in, guys. We'll catch you soon.